Recently, very important studies have been carried out on climate change. The first study with us says, how NASA's artificial intelligence and open science efforts combat climate change. As extreme weather events increase around the world due to climate change, the need for further research into our warming planet has increased as well. For NASA, climate research involves not only conducting studies of these events, but also empowering outside researchers to do the same. The artificial intelligence efforts spearheaded by the agency offer a powerful tool to accomplish these goals. In 2023, NASA teamed up with IBM Research to create an AI geospatial foundation model. Trained on vast amounts of NASA's widely used harmonized Landsat and Sentinel-2 data, the model provides a base for a variety of AI-powered studies to tackle environmental challenges. In keeping with open science principles, the model is freely available for anyone to access. Foundation models serve as a baseline from which scientists can develop a diverse set of applications, enabling powerful and efficient solutions. Foundation models only know what things are represented in the data. Once a foundation model is created, it can be trained on a small amount of data to perform a specific task. To date, the Interagency Implementation and Advanced Concept team, along with collaborators, have demonstrated the geospatial foundation model's capabilities by fine-tuning it to detect burn scars, to delineate floodwater, and to classify crop and other land use categories. Because of the computational resources required to create the initial foundation model, a partnership was necessary for success. In this case, NASA brought the data and scientific knowledge, while IBM brought the computing power and AI algorithm optimization expertise. The team's shared commitment to making their research accessible through open science principles ensures that their model can be useful to as many researchers as possible. To build a foundation model at scale, we realized early on that it's not feasible for one institution to build it. Everything we have done on our foundation models has been open to the public, all the way from pre-training data, code best practices, model weights, fine-tuning training data, and publications. There's transparency, so researchers can trace why certain things were used in terms of data or model architecture. Following on from the success of their geospatial foundation model, NASA and IBM Research are continuing their partnership to create a new similar model for weather and climate studies. They are collaborating with Oak Ridge National Laboratory, Nvidia, and several universities to bring this model to life. This time, the main dataset will be the Modern Era Retrospective Analysis for Research and Applications, version 2 meters E. RRA2, a huge collection of atmospheric reanalysis data that spans from 1980 to the present day. Like the geospatial foundation model, the weather and climate model is being developed with an open science approach and will be available to the public in the near future. Covering all aspects of Earth science would take several foundation models trained on different types of data sets. However, those future models might someday be combined into one comprehensive model, leading to a digital twin of the Earth that would provide unparalleled analysis and predictions for all kinds of climate and environmental events. Whatever innovations the future holds, NASA and IBM's geospatial and climate foundation models will enable leaps in Earth science like never before. Though powerful AI tools will enhance researchers' work, the team's dedication to open science supercharges the possibilities for discovery by allowing anyone to put those tools into practice and pave the way for groundbreaking research to help better care for the planet.
The second study with us is about NASA's efforts to combat climate change. Everyone on Earth is touched by the effects of climate change, such as hotter temperatures, shifts in rain patterns, and sea level rise. Collecting climate data helps communities better plan for these changes and build more resilience to them. The International Space Station, one of dozens of NASA missions contributing to this effort, has multiple instruments collecting various types of climate-related data. Because the station's orbit passes over 90% of Earth's population and circles the planet 16 times each day, these instruments have views of multiple locations at different times of day and night. The data inform climate decisions and help scientists understand and solve the challenges created by climate change. While crew members have little involvement in the ongoing operation of these instruments, they do play a critical role in unpacking hardware when it arrives at the space station and in assembling and installing the instruments via spacewalks or using the station's robotic arm. One investigation on the orbiting lab that contributes to efforts to monitor and address climate change is ECO System Spaceborne Thermal Radiometer Experiment on Space Station. It provides thermal infrared measurements of Earth's surface that help answer questions about water stress in plants and how specific regions respond to climate change. Research confirmed the accuracy of COSTRESS surface estimates 1 and found that the process of photosynthesis in plants begins to fail at 46.7 degrees C. Average temperatures have increased 0.5 degrees C per decade in some tropical regions, and temperature extremes are becoming more pronounced. Rainforests are a primary producer of oxygen, and without sufficient mitigation of the effects of climate change, leaf temperatures in these tropical forests soon could approach this failure threshold. The total and spectral solar irradiance sensor measures total solar irradiance and solar spectral irradiance. TSI is the total solar energy input to Earth, and SSI measures the sun's energy in individual wavelengths. Energy from the sun drives atmospheric and oceanic circulations on Earth, and knowing its magnitude and variability is essential to understanding Earth's climate. Researchers verified the instrument's performance and showed that it made more accurate measurements than previous instruments. TSIS maintains a continuity of nearly 40 years of data on solar irradiance from space-based observations. The Global Ecosystem Dynamics Investigation observes global forests and topography using light detection and ranging. These observations could provide insight into important carbon and water cycling processes, biodiversity, and habitat. One study used GEDI data to estimate pantropical and temperate biomass densities at the national level for every country observed and the subnational level for the United States. Earth's surface mineral dust source investigation determines the type and distribution of minerals in the dust of Earth's arid regions using an imaging spectrometer. Mineral dust affects local warming and cooling, air quality, rate of snowmelt, and ocean plankton growth. Researchers demonstrated that data from MIT also can be used to identify and monitor specific sources of methane and carbon dioxide emissions. Carbon dioxide and methane are the primary human-caused drivers of climate change. Increasing emissions in areas with poor reporting requirements create significant uncertainty in the global carbon budget. A high spatial resolution of MIT data could allow precise monitoring even of sources that are close together. The station's orbiting Carbon Observatory 3 collects data on global carbon dioxide during sunlit hours, mapping emissions of targeted local hotspots. This type of satellite-based remote sensing helps assess and verify emission reductions included in national and global plans and agreements. Monitoring by OCO3 and the Italian Space Agency's precursor Aperspectrale della mission applicative, a satellite of 30 coal-fired power plants between 2021 and 2022, showed agreement with on-site observations. This result suggests that under the right conditions, satellites can provide reliable estimates of emissions from discrete sources. Combustion for power and other industrial uses account for an estimated 59% of global human-caused carbon dioxide emissions. The Stratospheric Aerosol and Gas Experimenter measures ozone and other gases and tiny particles in the atmosphere called aerosols that together act as Earth's sunscreen. The instrument can distinguish between clouds and aerosols in the atmosphere. A study showed that aerosols dominate Earth's tropical upper troposphere and lower stratosphere, a transition region between the two atmospheric levels. Continuous monitoring and identification of these layers of the atmosphere helps quantify their effect on Earth's climate. An early remote sensing system, ISSSE, RVIR Environmental Research and Visualization System, automatically took images of Earth to help scientists assess and monitor disasters and other significant events. Researchers reported that this type of Earth observation is critical for applications such as mapping land use and assessing carbon biomass and ocean health.
The last study with us says NASA's Near Space Network enables PACE climate mission to phone home. The PACE mission has delivered its first operational data back to researchers, a feat made possible in part by innovative data storing technology from NASA's Near Space Network, which introduced two key enhancements for PACE and other upcoming science missions. As a satellite orbits in space, its systems generate critical data about the spacecraft's health, location, battery life, and more. All of this occurs while the mission science instruments capture images and data supporting the satellite's overall objective. This data is then encoded and sent back to Earth via radio waves through NASA's Near Space Network and Deep Space Network, but not without challenges. One challenge is extreme distances where disruptions or delays are common. Satellite disruptions are similar to what internet users experience on Earth with buffering or faulty links. NASA's Near Space Network integrated DTN into 4 new antennas and the PACE spacecraft to showcase the benefit this technology can have for science missions. The network, which supports communications for space-based mission within 1.2 million miles of Earth, is constantly enhancing its capabilities to support science and exploration missions. PACE, a satellite located about 250 miles above Earth, is collecting data to help researchers better understand how the ocean and atmosphere exchange carbon dioxide, measure atmospheric variables associated with air quality and climate, and monitor ocean health by studying phytoplankton, tiny plants, and algae. While PACE is the first operational science user of DTN, demonstrations of this technology have been done previously on the International Space Station. In addition to DTN, the Near Space Network worked with commercial partner Kongsberg Satellite Services in Norway to integrate 4 new antennas into the network to support PACE. These new antennas allow missions to downlink terabytes of science data at once. Just as scientists and engineers constantly improve their instrument capabilities, NASA also advances its communication systems to enable missions near Earth and in deep space. If PACE orbits Earth, it will downlink its science data 12 to 15 times a day to 3 of the network's new antennas. Overall, the mission will send down 3.5 terabytes of science data each day. Network capability techniques like DTN and the 4 new antennas are the latest enhancements to the Near Space Network's catalog of services to support science missions, human spaceflight, and technology experiments. In addition to these new capabilities, the network is also increasing the number of commercial antennas within its portfolio. In 2023, NASA issued the Near Space Network Services request for proposal to seek commercial providers for integration into the network's expanding portfolio. With an increasing capacity, the network can support additional science missions and downlink opportunities. Thank you very much for watching. Goodbye.